Good morning. Actually, my student, Gino Andrade, he should be here, but he graduated about 1 month ago. He finished his master's, and he lives in another city, and so I'm presenting his work, which was done together with Renato, and this is the use of particle filters to estimate relative airspeed in a pitot tube. Okay. So this is the summary of the presentation. We have the motivation, the physical problem and mathematical formulation, the direct problem and the inverse problem associated with this, the mathematical formulation of this physical problem. I'm going to talk a little bit about state estimation problems and its solution through the particle filters, results and conclusions. The motivation we all know, it's the it has to do with the formation of ice in pitot tubes, but actually what we are trying to see here is the feasibility of having an alternative estimation of the airspeed when the pitot tubes go into icing conditions. So this is the model that we use. This is the same one that you have already seen a couple of times. This is the formulation of the physical problem. We use improved Lampard formulation based on the couple integral equations approach, where all those functions they are known. Kleber has just presented them. Here it's the boundary condition. It's a convective boundary condition at the tip of the pitot tube, where we have this heat transfer coefficient between the pitot tube and the incoming air. For the lateral surface and also for the tip, we take into account the dissipation effects through the adiabatic wall temperature. And for the lateral surface, we use regular heat transfer coefficient Nusselt number correlations. So the direct problem was, for the direct problem, we assume that all the quantities that appear in the model, they are known. And for the solution of the direct problem, we have used the finite difference. So it was written in this typical form. And but for the solution of the inverse problem, the objective here is try to identify the relative airspeed if by using transient temperature measurements taken within the pitot tube. So this can serve as an indirect measurement of the airspeed through an inverse heat transfer analysis, and which can be like another measurement of the airspeed, and it can be the measurement of the airspeed if there is like if we cannot count with the measurement of the pitot tube during the formation of ice. And besides estimating the airspeed, we also try to estimate the formation of ice at the tip of the pitot tube through the identification of that heat transfer coefficient, which is expected to have a sudden drop because of the increasing heat transfer thermal resistance at that point when the ice is formed. Okay, so since this is intended to be done sequentially and hopefully one day online, we have to solve a state estimation problem. This state estimation problem, it involves two models. One is the state evolution model, which evolves the state variables x from time tk minus 1 to time tk. This can be a nonlinear function of these state variables and this input function, these input variables. And we also need to make use of an observation model, which is give us the physics, all the physics related to the variables that we can measure. Both models are stochastic. V is the noise associated with the state evolution model, and N is the noise associated with the measurements. And so the objective here is to estimate the state variables by using all the available information that we have. So it's the mathematical formulation of all the physical problems involved in the evolution of those state variables, and all the physical processes that are involved in the measurements themselves. There's some statistical hypotheses that I'm going to move on. But so basically related to the state estimation problem, we can have different kinds of problem. One of them is the prediction problem. Okay, so the prediction problem, we aim at estimating statistical distribution of the state variables given the measurements up to the previous time. And but we have the filtering problem, which is basically the estimation of the distribution of the state variables given the measurements up to that specific time. But we can also think about what's called a smoothing problem, which is like using measurements at future times in order to obtain estimates at the time that we are worried about. Okay. So here I'm only dealing with this filtering problem. So basically, we have to assume that we know the statistical distribution function of the state variables at some time t0. And the solution of the filtering problem is done in two steps, this prediction and update steps, which are illustrated here. So in order to get a prediction, we evolve from time 0 to time 1 by using the evolution model. Then we get a prior information about these state variables at this time t1, and now we bring the information given by the measurements at that same time t1 through a likelihood function, and then we update the estimates to get a posterior distribution at the time of the state variables at time t1 given the measurements at the same time t1. So this is basically a Bayesian procedure. And when the evolution and the observation models are linear and the uncertainties, they are additive and Gaussian, we can apply the Kalman filter. And the Kalman filter actually, it results in optimal solutions for this problem in the sense that we get minimum variance and unbiased estimates of the state variables. However, many of the problems that we deal with, and actually the problem that we are of the estimation of the airspeed, these models are non-linear. Okay, and although exist extensions of the Kalman filter for non-linear, non-Gaussian problems, what appears in the literature to be the most general techniques are Monte Carlo techniques. They are sequential Monte Carlo techniques. And basically what you have to do, you try to represent your distribution function in terms of samples of this function, which are called the particles. That's why the name particle filter. Okay, and then you get some statistics. You can get some statistics of the distributions by using the values of those particles of the samples and also some weights associated with them. Okay. This is illustrated in this picture, which actually represents the algorithm that we have used. It's a very basic algorithm for those particle filters, which is called sample importance resampling algorithm. Okay, so here we have the particles already evolved from time k minus 1 to time k. Okay, so the weights for the particles, they are given by the likelihood. Okay, so all the information provided by the measurements now comes here to give the weights for each particle. And And then we get these posterior estimates. Okay, so this methodology developed in the 50s. One usual problem is that as time evolves, you might have one or few particles with large weights and a lot of particles with very small weights, and you're not willing to represent a distribution function, a statistical distribution function with only few particles. Okay, so this and another problem is that you spend a lot of computational time to advance particles with negligible weight. So what has been done was the introduction of this resampling step. And in this resampling step, you basically neglect particles with low weight, okay, and you replicate particles with large weights. Okay, so in the sense you try to give some variability, increase the variability of the particles. So this is the algorithm. Okay, it's a very standard algorithm. It's not difficult to code. And now let's move to our cases. So in our case, the state variables are given by the vector of temperatures in all node points in the finite difference grid that we have selected to work. And we also have as state variables the heat transfer coefficient at the tip of the P2 probe and the air velocity. Okay, so they are all time variable functions. So we have a model to advance the temperatures, okay? For this model, we have assumed that the uncertainties are additive and Gaussian with zero mean and a standard deviation of 1% of the temperature value. But we don't have models to advance these two variables. So in this case, we basically use random walk models, okay, in this form. And this was the first examples that we tried. So we tried to estimate the heat transfer coefficient with a function that suddenly drops, and this would be caused by the formation of ice at the tip of the P2 tube. Okay, and we after the P2 tube, you cannot rely on the measurements of the P2 tube. Then we checked different variations of velocity. Okay, and this was all done by simulated measurements, and the simulated measurements are also Gaussian with zero mean and a standard deviation of 5% of the maximum temperature value. Okay, so this would be the exact functions at two measurement positions at the P2 tube. Okay, so this is very close to the tip of the P2 tube, and this one is more on that cylindrical region of the P2 tube that Kleber has just shown. Okay, and this would be the temperature variations for these three different cases. Okay, an interesting thing is that actually the noise that we are simulating here for the measurement it's quite high. You can see here that this would be the temperature increase resulting from the formation of ice at the tip of the P2 tube. Okay, but actually the noise level is much larger than this temperature increase. Okay, so when we try to estimate, I'm sorry that the pictures were okay on my computer, and here that they are kind of strange. But these are the exact functional forms for the heat transfer coefficient. Okay, the estimates are given those red strange symbols, and the blue lines give the 99% confidence intervals. Okay, so we can see that the uncertainties related to the estimation of the heat transfer coefficient, they are very high, and there are also some occasions that we can't even detect the dropping of the heat transfer coefficient at the P2 tube. Okay, so this is actually what it means that it's difficult to detect the formation of ice in the front of the P2 tube through the temperature measurements, at least with such large noise that we have considered here. Okay? I'm not going to present results, but if this noise is made very small, then we can we can actually recover the heat transfer coefficient better. Okay? On the other hand, we can see for this example, for a step variation, for a triangular variation here, and also for like a door variation here for the velocity, the estimations obtained with the heat the solution of the particle filter, okay, they are very good. Okay, they are very good. This was done by 500 particles. And I'm going to comment a little bit later about the CPU time and things like that. Okay. The other case that we have run was considering the stall of the Airbus. Okay, so we thought about a test case that the stall would come from the normal cruise speed, okay, of 276 meters per second. And this would suddenly drop to a very dangerous situation of stall of 87 meters per second, and this is with flats up. Okay, and we assume that this could happen in 30 seconds. Okay, so for the simulated measurements, we have additive Gaussian noise with 1 degree centigrade of standard deviation. For this solution, we have used 500 particles. So these are the measurements and the exact temperatures and the measurements and also the estimates at 2 different measurement positions. Okay, this is also very close to the tip of the probe, and this is in the cylindrical region. And we can see that we can estimate the state variables for which we have measurements very well. Our interest, of course, is not on the temperatures themselves, but it's on the heat transfer coefficient and on the airspeed. And again, although we can eventually recover the heat transfer coefficient at the tip of the probe, thus characterizing the formation of ice at the tip. Okay, this is still done with a large uncertainty, and there are cases that we can't even get to this value of small heat transfer coefficients. Okay. On the other hand, we're very happy with those results. That we can see here that this is the variation from the cruise speed to the stall speed, okay, in 30 seconds, okay, and we can actually get an estimate of this speed, okay, although the uncertainties here are still large. So some conclusions, this algorithm, and this is actually a very, very basic algorithm of these particle filters. We did not test any more recent and actually computationally more performant algorithm for this case, okay? We were only trying to see if this concept could work. And the concept can work, as we see, but we still have some problems to deal with, that the computational times are large. Okay, so for 500 particles, this took about 5 hours on an i7, but this was done without any object of improving the computational performance. Okay, this was done on the Mathematica. It was not done with any kind of parallelization or with anything like that. Okay, so we still need to develop some faster codes on faster computational platforms, examine other particle filter algorithms, and also try to see if these uncertainties can be decreased by increasing the number of particles. This is usually the case, okay? Generally with this algorithm, with a small number of particles, we can get a good estimate of the mean of the state variables, as we are getting here, okay? But we need a lot of particles to have a good estimate of the uncertainties associated with the state variables. So this is something that we have to deal with the effect of the number of particles on the accuracy of the estimated state variables. Okay, but at least with 500 particles, we could get a very good estimate of the mean of the variable, which might already be a very, very useful information in the case that you don't have any speed measurement from the pitot tool. Okay, so this concept of having an alternative indirect measurements of the speed through the solution of an inverse heat transfer problem through the use of temperature measurements, this have a potential to work. Okay, and this is some acknowledgements. Also, I'd like to thank the organizers for inviting my student and me, of course, to speak today. Thank you.